this example, I have a large drum with a string wound around it and a mass A hanging off that string off this big drum. And the mass A has a weight of 10 pounds. The drum is a solid cylinder with a mass of 30 pounds and a radius of 0.8 feet. And my question is, what is the acceleration of A in this system? And this is actually a really similar system with a little bit of different information that we actually use to measure moments of inertia of things that are rotating. So big flywheels or car wheels and things, when we really want to know how good of a job did we do figuring out the moment of inertia or creating what we wanted. We use a very similar setup, hanging masses that are accelerating bodies to figure out what their radiuses of gyration are and their mass moments of inertia. So not an uncommon setup. In this case, we have kind of coupled motion, so we should be thinking about our coupled motion, and we also have rotating masses and linearly moving masses. So there's a few different systems we're going to have to couple together here. And I'm going to start by looking at just A, because A is very similar to what we've done before. If I draw a free body diagram of A, I have the tension pulling it upwards, and I have the force of gravity pulling it downwards. So just to figure out the acceleration of A, I can easily do some of the forces on A is the mass times acceleration of A, and in this case I've done it in the vertical direction. My forces are tension minus the force of gravity, so mg will equal the mass of A times the acceleration of A. And this is great, we know mass, we know gravity, we're trying to find acceleration, but we don't know the tension. So unfortunately that isn't quite enough information to solve, but it's a pretty good start. So now I'm going to do similar thing with B. So for the big object B, if I draw a free body diagram of this, I know I have a tension off over here. I have a force of gravity. And then I also have another kind of bigger, I'll call this T2 tension force that's holding it up to the top. So I know it's not really moving, so if I did the sum of the forces of all of these, I should end up with 0, but it does rotate. So the sum of the moments is not going to necessarily equal 0. So I'm going to do sum of the moments equals I alpha. And anytime I do sum of the moments, I have to decide what axis I'm going to do it about. And since I don't need to figure out any information about T2, I'm going to go ahead and do it about the center of mass, O, and then I don't have to worry about that second tension force or the gravity force. I only have to worry about the tension that's connecting to the block A. Just super convenient. So if I do it about O, the only thing causing a moment is this tension force. So tension moments are a force times a distance, and I'm just going to do times R. And I'm going to go ahead and do the cross product in my head, and I am going to get a positive moment. Again, thinking that it's pulling it this way, my fingers are curling this way using my right hand rule. That's going to be a positive K hat moment. So I'm going to go ahead and just leave this as the tension times the radius, and that'll equal my mass moment of inertia times the angular acceleration, alpha. So again, I don't know my tension, but I do know my radius. I don't know my mass moment of inertia, and I don't know my alpha. So that didn't help that much. But if we go back to our original problem statement, I think I have enough information to figure out my mass moment of inertia. It says it's a solid uniform cylinder. If I look at my table of mass moments of inertia for solid uniform cylinders, I'll see that the mass moment of inertia about the center, in this case, is 1/2 mr squared. That's all information I know, so I can actually calculate the mass moment of inertia of B is 1/2 the mass of B. I could use pounds here, but if I think farther ahead, pounds aren't going to work, so I'm going to go ahead and convert to slugs. Another reason, when in doubt, convert to slugs. 32.2 slugs, and then times my radius 0.8 feet squared. Or we could just leave it in variable form, which is actually what I did in my solution, so I don't have this exact number, but you could calculate it. All right, so now I know my I, about 0, about the center for B, and that's about the center. And so I still have 3 unknowns here. I have an unknown tension force, an unknown acceleration of A, and an unknown angular acceleration of the cylinder B. But Recall, this is a coupled motion problem. So how A moves is actually directly related to how B moves. And we might recall that this is actually going to be, they're going to be coupled here. The tangential motion of B at that coupling point has to equal the acceleration of A. So the tangential acceleration of B will have to equal the acceleration of A because of that thing. And the tangential acceleration, remember, is alpha r. And so here now I finally have a third equation, and this gives me my 3 unknowns. So now I have enough information, 3 equations, 3 unknowns to solve this problem. So just to put it all into the formulas to check to make sure everything's going to work, here I have unknown tension minus mass. When in doubt, convert to slugs, and this is the prime case to convert to slugs, so 32.2, 10 divided by 32.2 slugs, times 32.2 feet per second squared should equal 10 divided by 32.2 slugs times my unknown acceleration of A. And if I check my units out here, I have slugs, feet per second squared, slugs, so my acceleration should be in feet per second squared, and my tension should be in slug feet per second squared. And remember, a slug foot per second squared is a pound, so that actually makes sense. This will be in pounds, and this will be in feet per second squared. All right, coming back up to my B equation, my unknown tension should be in pounds times my radius is 0.8 feet, so that'll give me foot-pounds, is my mass moment of inertia, so this is slug feet squared. 30 divided by 32.2 slugs, 0.8 feet squared times my alpha. So if this, I have foot-pounds. Remember, a pound is a slug foot per second squared. So I'll have slug feet squared per second squared. Here I have slug feet squared, which means my alpha will have to be per second squared. So that'll be radians per second squared, which makes sense. And then coming down to my final coupling equation, I'll have my alpha, which should be in radians per second squared, times my radius is 0.8 feet, will equal my acceleration, which would then be feet per second squared. That all makes sense, so everything works out here. And what I get for my final acceleration of A is 12.88 feet per second squared. And if you want to, you can also solve for the other unknown variables. The tension I got is 6 pounds, and the angular acceleration of the cylinder B I got is 16.1 radians per second squared. So another example here of how we can use sum of the moments is equal to I alpha in solving kinetics problems in dynamics, especially when we have size, shape, and rotation.